let's just quickly fire off a couple corollaries to the Euclidean algorithm and Bezout's theorem of the previous video. So the first thing we're going to prove, corollary 1, is that if some integer d divides a product of integers a and b, and a and d have GCD equal to 1, then it's going to turn out that d divides b. To see this, Bezout's theorem tells us that since a and d have GCD equal to 1, there exist some integers x and y, so that ax plus dy is equal to 1. And if I multiply both sides of this by b, I'm going to get that a times b times x plus d times b times y is equal to b. Well, I know that d clearly divides d times b times y, because there's a d in the factor there. And by assumption, d divides a times b. So that means that d divides the sum, that is, d divides a times b times x plus d times b times y. But as we can see from the equation, that's just the same thing as b. And we get our conclusion that d divides b. For the second corollary, we're now going to suppose that we have two integers a and b, and that their GCD is d. And we're going to suppose that there's another integer, c, such that c divides a and c divides b. And we're going to conclude that c divides d. Again, this is going to follow from an application of Bezout's theorem, because Bezout's theorem tells us exactly that we have a pair of integers x and y, so that ax plus by is equal to d. And again, c divides a, so it divides a times x. C divides b, so it divides b times y. In other words, c divides a times x plus b times y. And again, we've seen that's just the same thing as c dividing d. For the final corollary, coming from Euclid's algorithm and or Bezout's theorem, we're now going to suppose that a divides some integer m, b divides that same integer m, and that a and b have GCD equal to 1. Perhaps I've mentioned this in another video, perhaps not, but we also call this coprime, because they share no common factors. We also say relatively prime as well. So in this case, we're going to conclude that a times b divides m. So for our proof, well, since b divides m, we know that m is equal to b times q for some integer q. And since a divides m, we know that writing a divides m, replacing it with b times q, this says that a divides b times q. But the GCD of a and b is equal to 1. So by our first corollary, we know that since a divides b times q and the GCD of a and b is 1, it must be the case that a divides q. In other words, we can find some integer so that q is equal to a multiplied by r. And finally, writing m as b times q, And rewriting the Q as A times R, we see that M is equal to B times A times R. And finally, we conclude that A times B divides M.